The ionization energy is the amount of energy that we need to add to take an electron away from an atom or an ion. This is done in the gas state, and it is an endothermic process, which means we have to put energy into taking that electron away. So valence electrons are the easiest to move. They have the lowest ionization energy, and we abbreviate ionization energy IE. So when we're taking valence electrons away, it's pretty easy. We do have multiple ionization energies that we can look at. So every time we take an electron away, that is another ionization energy. So if we're taking an electron away from a neutral element, that would be our first ionization energy. If we're taking an electron away from a cation with a +1 charge, that would be our second ionization energy. So the energy that we need to take an electron away from an element or ion. If we look at the trend to take that first electron away from a neutral element, the larger the effective nuclear charge, the harder it is to take the electron away from it, the more energy we need to put in. Remember, effective nuclear charge is the amount of attraction that those valence electrons have towards the nucleus. As we go to the right on the periodic table, our effective nuclear charge increases. The further away the electron is from the nucleus, the easier it is to take the electron away. So essentially what this is saying is that our ionization energy trend is opposite of our atomic radius. If we go up the group, our first ionization energy increases. Our valence electrons are held closer and tighter to the nucleus. As we go to the right, across the period, our ionization energy increases because our effective nuclear charge increases. And so our general trend for our first ionization energy, it increases as we go up and to the right on the periodic table. This opposes the size of our atomic radius. You will notice that as we go up and to the right on the periodic table, we do get a general increase in first ionization energies. There is a few elements that go against this trend, like nitrogen and oxygen, beryllium and boron, and we'll talk about why that is in just a minute. Choose the atom in each pair with the larger first ionization energy. If we look at aluminum and sulfur, so aluminum and sulfur, the sulfur is further to the right, so that would have the larger first ionization energy. If we look at arsenic and antimony, so arsenic is 33, antimony is 51, so arsenic is further up the periodic table. It would have a higher first ionization energy. If we look at nitrogen and silicon, nitrogen is further up and to the right than silicon, so it would have the larger first ionization energy. How about oxygen and chlorine? Well, these are opposing each other, so it's difficult to tell which would have the larger first ionization energy just looking at our general trend. So this one is difficult to tell. We do have a couple exceptions to our first ionization energy trend. So they generally increase up and to the right. However, if we look at Group 2 and Group 3, Group 5 and Group 6, we see some discrepancy. If we look at our boron and beryllium, which one do you think would be easier to take the electron away? Well, our boron is going to be slightly easier to take the electron away because we have a single electron in the p orbital. It's a little bit harder to take the electron away from a completely filled orbital like beryllium has. What about if we look at nitrogen and oxygen? Which one is going to be easier to take the electron away? The first paired electron in oxygen is going to be slightly easier. Our nitrogen gains some extra stability from having a half-filled p orbital. This is why these oppose the trend a little. We can also look at successive ionization energy. So as we continue to take more and more electrons away, every time we take an electron away, it costs more energy. We have to add more energy in to get that next electron off. This is partially because we have more protons than electrons, and so those electrons are getting closer and closer to the nucleus and harder to remove. We do see regular small increases in ionization energy while we're removing valence electrons. As soon as we start moving core electrons, then we get a very large jump in our ionization energy. So for sodium, we can remove one electron fairly easily, and then we get a very large jump when we remove the second electron. For magnesium, we can remove two, and then we get a large jump because we're removing a core electron. And so this allows a stair step to be observed between ionization energies when we start removing cores. So we get a big jump in ionization energies when we start removing core electrons. Valence electrons are relatively easy to remove, but core electrons are significantly harder. That's why there is a large jump between the energies of the valence electrons versus the core. So as we've moved through this chapter, as always, there's problems that you can use to help check your comprehension of these topics.